I guess we're live. Hello, everyone. Welcome to Astronomy on Tap. Today we will have Cristina Schlesier talking to us about the new result from the Muon G-2 experiment at Fermilab. So a couple of decades ago, an experiment conducted at Brookhaven National Lab measured the magnetic moment of muon and found that it was off the standard model prediction by 3 standard deviations. So now Cristina will talk about a new measurement of the same experiment, this time done at Fermilab. Cristina is a PhD candidate at the University of Illinois. She's from New Jersey, and she's also active with Education Justice Project program on campus. I'm Adi. I'm also a PhD candidate in the Department of Physics. So now, without further ado, I'll hand it over to Cristina.
Thanks, Adi. And thanks everyone for tuning in. Yeah, so let's get right into it. As Adi said, I'm a member of the Muon G-2 collaboration at Fermilab, which is an experiment that's generated a bit of excitement in the past few weeks. And my goal with this talk is to hopefully put that excitement into a bit of context. So let's get into it. Okay, so on April 7th, just a few weeks ago, after lots of secret meetings and emails and press releases bouncing around the collaboration, we released our first result from our first year of data taking. And this highly anticipated result unleashed quite a bit of buzz from the physics community and also national news outlets. We even got a little shout out in the local press. And for the Star Wars heads, we got a shout out from Luke Skywalker. So needless to say, many people consider this a big deal. But why? So before I get into the experiment and the result and what that all means, I'm going to lay out a bit of a foundation. So I'll talk about contemporary physics and sort of the theoretical framework for all of this and the motivation for the experiment. And then we'll end with some interpretation of what it means and what's next. Okay, the standard model, what is that? So yeah, some people have heard of this, some people have not. I think if you've never heard that phrase before, it sounds very vague. Standard model are just these like generic, non-specific words that don't sound like scientific jargon. But in the physics world, the standard model, or the standard model of particle physics, is the name for our theory of almost everything. So how does the standard model fit in with the rest of physics? If we think about physics as just sort of describing how stuff works and also giving us the math to tell us how stuff works, then particle physics tells us about how fast and small stuff works. So in this little cartoon thing here, we have these axes, size, and speed, and these are fundamental observables. Our ability to understand these observables at different scales is part of the history of physics. So if you go back in time to when classical mechanics was kind of like the only physics on the scene, it's generally associated with Isaac Newton. We can use this formulation, classical mechanics, to predict the motion of large, slow things like planets in orbit, or cars driving around, or boats, sailing in the ocean. And this is kind of like where we live. This is the rules of classical mechanics more or less govern our ordinary experiences. However, when things speed up, meaning approach the speed of light, so very speed up a lot, classical mechanics breaks and we need another formulation. That's relativity. Similarly, when we shrink down to the subatomic realm, classical mechanics doesn't work there either, and that's where quantum mechanics comes in. So when we combine quantum mechanics and special relativity, we get particle physics, fast stuff and small stuff. And the mathematical framework of particle physics is quantum field theory, the set of quantum field theories that describe 3 of the 4 forces in nature make up the standard model. Okay, so here is, I just love these like old retro posters. I used to think they were really cool before I studied physics. But But anyway, this one is pre-Higgs boson discovery, so it's kind of a fun historical artifact. This is the more modern representation of the Standard Model. So you see the Higgs in the middle there. And basically what it is, it shows you all the particles in the model, and then not represented here, but represented in equations. They're sort of like the rules of how they interact with each other. And like I said before, the Standard Model is a theory. It embodies all of our current understanding of these fundamental particles and 3 of the 4 forces. And according to the Standard Model, quarks and leptons are the building blocks of matter. So that's the outer ring here, the orange and the green. And the forces interact through carrier particles called bosons. And those are the blue. So you have the photon, which is the carrier for the electromagnetic force. And then you have the other bosons for the other nuclear forces. So then the forces, I keep saying 3 of the 4 forces. So which 3 are the ones that are covered in the Standard Model? It's the first 3. The strong nuclear force, the electromagnetic force, and the weak nuclear force. One interesting thing about contemporary physics is how each of these forces have very different strengths. So if we give the strong force strength 1 in arbitrary units, then we can compare the other forces. So the electromagnetic force by comparison is 100 times weaker. The weak force is 1,000 times weaker than that. And the gravitational force is so much weaker. Like, yeah, I don't actually know what the name of that number is, but it's very, very weak. And I think this surprises people when they learn about this, that gravity is actually the weakest force, because that's the one we're most accustomed to. And we think about, like, you know, falling off your bike or whatever, dropping something on your foot. Gravity definitely feels very strong. So there is some sense that the top 3 forces, the ones that are included in the Standard Model, are all different expressions of the same force, just at different energy scales. In fact, electromagnetism was once viewed as 2 separate things, electricity and magnetism, and they're now understood to be the same. They're both mediated by the photon. The weak force has been unified with the electromagnetic force in what is known as electroweak theory. So there's like this pattern of these forces sort of having something in common. Let's see. Okay. So if the Standard Model only describes the top 3, then what describes gravity? That would be general relativity. And I'm not going to say really anything about gravity other than, if you've heard of things like string theory or quantum gravity, those are attempts to reconcile theories of gravity with the Standard Model, or with, you know, with these other 3 forces. And that's very much outside the scope of this talk, which is an interesting thing about the Standard Model. And like I mentioned before, gravity is super weak. And not only is it weak, it's just so much weaker than the other forces. This huge discrepancy between the weak force and gravity is called the hierarchy problem. And it's one of several unsolved problems in physics. So this is just a good segue into this fact that even though the Standard Model has been verified many times over by experiments and is super powerful and predictive, it also leaves many questions open, such as, why is gravity so weak? What's the nature of dark matter and dark energy? Why does the Standard Model have 18 free parameters? And why is there more matter than antimatter in the universe? There are lots of questions like these. So that's something to keep in mind. Okay, so we have the particles, which are shown in that circular chart, and we have the forces. How do they combine and manifest in space? I mentioned before that the Standard Model is a quantum field theory, meaning the objects we consider are not exactly like isolated particles or waves, but rather they are excitations of a quantum field. In other words, each one of these so-called particles are actually fields that fill all of space. So when we observe a particle, we're observing a coherent fluctuation of that field. You could think of it kind of like a ripple in a pond. So like the surface of the water is the field. And then when you have a bump in that surface, that is, you could think of that as that packet of water as like a particle. Okay, so each of these particles corresponds to a field that permeates all of space-time, and you can imagine all of space filled with this stack of fields, and they're all interacting with each other, and they're all kind of like doing quantum stuff. So this seems kind of complicated, right? And like spooky, and why would I bring this up? And the point I'm trying to make is that the vacuum isn't really empty. So when particles move through space, they're interacting with all this stuff, all these quantum fluctuations that are permitted by Heisenberg's uncertainty principle. And you'll often hear these quantum fluctuations referred to as virtual particles, which virtual in this case doesn't mean that they aren't there. They actually are there, but they exist for such a short amount of time that we can't directly detect them. Okay. So does that make sense so far? I hope so. I'm going to shift gears for a second, but just keep all that stuff about the vacuum in the back of your mind. So here we have a few magnetic field configurations. So a set of poles, a loop of current, and a dipole. The magnetic dipole is the limit of these previous two cases, meaning if you take the poles and you bring the north and south, shrink the gap between them and bring them together, shrink the gap to 0, you'll get a dipole. Or if you take the loop of current and you shrink the area it encloses to 0, you'll also get a dipole field. Each of these configurations has something called a magnetic moment. I think if you've ever held a bar magnet in your hand or just a strong magnet and you kind of feel the torque of it when you're moving it around relative to some external field or like a piece of metal, something like that, that's the torque. That's the system's natural tendency to align the magnetic moment with the external field. For a dipole, there we go. For a dipole, the torque causes the magnetic moment to precess around the field at a rate that depends on the strength of the magnetic moment and the strength of the external field. So if we have a charged particle, we can think of this as a dipole. One way of thinking about it, which isn't exactly correct, but it's helpful to illustrate, an electron, it has a charge, and if you think of it as spinning around, it's kind of like what a loop of current is doing. It's taking a charge and putting it on a circular track, right? So we get a magnetic moment. Now, this, thinking about it in this way, like I said, it's not exactly correct because the electron is a point particle. It doesn't have spatial extension. So rather than angular momentum, that like a macroscopic object would have, say a spinning top, gyroscope, something like that, the electron actually has the quantum mechanical version of angular momentum, which is called spin. And thinking about spin in this classical way, it underestimates the magnetic moment of the electron by a factor of 2. So historically, this factor of 2 was named the G factor and became part of the definition of the electron magnetic moment when these things were first being studied like 100 years ago. Now, when we treat both the electron and the field as quantum objects, the field becomes described by a photon and we get G equals 2. We get the correct factor back, more or less. Okay. But it turns out G actually isn't 2 either. It's slightly bigger than 2. Meaning that the electron spin is interacting with more than just the photon. So this is where those virtual particles that I mentioned before, they come back in to the story. It turns out that an electron in an electromagnetic field, it's not just interacting with the photon, but with all those fields that I mentioned before that permeate all of space-time, including itself. It's interacting with its own field as well. And most of the time, these other fields are quiet. But occasionally the quantum fluctuations generate particles that live just long enough to interact with our electron and disturb its precession before those particles disappear back into the vacuum. So in the 40s, Julian Schwinger calculated the first order self-interaction correction to this number, to this G factor for the electron magnetic moment. There it is. It's alpha over 2 pi. Alpha is the fine structure constant. And so you can see just this first order correction, it's a small number. So G is not 2, but it's not 3. You know, it's just a little bit more than 2. And yeah, this term alpha over 2 pi was such a major contribution to the field at the time, and still is really important. But it was engraved on his tombstone because it was such a major contribution. Okay, so hopefully that makes sense, but just to illustrate really what the difference is between, I hear my dog barking, to illustrate the difference between our understanding of like the world where G equals 2 and the world where G is greater than 2. What's the difference in those sort of two universes? So here, if G is 2, it's just interacting with the photon, spinning around, la-di-da. Okay, if G is greater than 2, which is the universe that we live in, we have the spin interacting with the photon, but also the virtual particles that pop up and then disappear. Right? Okay. And this is a measurable effect. That's why we know about it, because we measure a different G than we would if G was equal to exactly 2. All right. I'm going to pause here and see if there are any questions. And Adi will let me know if there are. Okay. So I've been talking about the electron a lot, even though this talk is about muons, right? But historically, a lot of these original developments concerning quantum field theory, particle physics, standard model, they were concerned with the electron because it was easier to study. And today, the magnetic moment of the electron is known to such a high precision that it's the most accurately verified prediction in physics. So to learn more, we have to turn to the muon. Okay, some stats. You'll usually see the Greek letter mu as the symbol for the muon. It was discovered in 1936. It has identical charge and spin to the electron. Unlike the electron, whose lifetime is, well, the electron is stable. We've never seen it decay. So the electrons, the official estimation is something like a zillion times the age of the universe. So by comparison, the muon lives much shorter. It decays, its lifetime is 2 millionths of a second. And there's also a difference with the mass. The muon is 200 times more massive than the electron, but still pretty light particle. Okay, some more fun facts about the muon. It was originally called the mesotron. When it was first discovered, it wasn't known to be a fundamental particle. We thought it was, physicists thought it might have had substructure like the proton or neutron. And well, I'll just say, I guess like maybe some people who are tuning into this talk hadn't even heard of muons before, which is totally understandable because muons are not part of the matter that make up our ordinary experience, our everyday experience, right? Like most things are made of protons, neutrons, and electrons. That's like the periodic table. So you don't really think about muons often. However, hundreds of muons do pass through your body every minute. And these muons are produced when cosmic rays pass through the atmosphere. Because muons pass through matter without leaving much of a trace, they can also be used kind of like X-rays to study the interiors of objects. There are a few cool examples of this, but my favorite one, and I've heard so far, I actually learned about this only recently. There is a team who found a hidden chamber in the Great Pyramid of Giza with the help of muon scanning, which I think is kind of fun. Okay, so back to G-2. Like I said before, I talked about G-2 in the context of the electron because that's sort of the historical way of talking about it. But we do this measurement now with the muon. And the reason we do that, well, the muon is the best candidate out of all the charged leptons. There are a few reasons for that. Like I said, the electron, it's already been measured to a really high precision. Also, the electrons, the contribution with the electron is dominated by quantum electrodynamics. So I haven't said this phrase before, but quantum electrodynamics is the part of the standard model that's concerned with electromagnetism. And that's the part that we understand the most. So studying the electron, there's not that much for us to learn because we have calculated that out to very, very high precision. With the muon, on the other hand, because it has a different charge to mass ratio, the muon actually probes other sectors of the standard model and is more sensitive to hadronic contributions, which means things that are concerned with the strong force. And that's the part of the standard model that we know less about. Also, it has a lifetime that with a boost, with a relativistic boost, we can make it live long enough to study, and the mass is within the reach of our accelerators. The tau lepton, on the other hand, so this is the kind of unknown relative of the other two. It doesn't get talked about a lot, but the tau lepton is 17 times more massive than a muon, so much harder to produce, requires a lot more energy, and has a way shorter lifetime. So even though the tau would be interesting to study in terms of the sectors of the standard model that it is sensitive to, it's, I think, prohibitively difficult to do so. All right. So Adi, I think, teased this in the beginning that there was an experiment at Brookhaven National Lab on Long Island in the early 2000s, and they measured G-2 for the muon, and they found some discrepancy between the standard model prediction. Now, we aren't yet at the level of claiming a discovery. This 3.6 sigma, this is kind of a scientific shorthand for how confident we are that it's like a real effect and not a statistical fluctuation. So the discovery gold standard is 5 sigma. This one here is 3.6, so it's not quite there yet. But anyway, what do we do with this information, right? This is like tantalizing, but it's not confirmed new physics yet. Of course, we consider the possibility that we made a mistake. That's always possible with science because human error is a thing. But we have reason to be confident in the measurement. And even since this calculation came out on the standard model side, there's more consensus being built. So the more exciting possibility is that both the measurement and the theory were done correctly. And that necessitates that the theory is missing a piece and that the measurement is shining a light on that missing piece. Okay. Before we get into the experiment, I'm going to pause again and see if there's anything burning in the chat.
We have a couple of questions now, actually.
Uh-oh.
So Melanie asks in the chat, have virtual particles ever been detected? And if they exist too short a time, how do people know they're there? Is anyone trying to detect them?
So, well, the thing is like I said before, we don't detect them directly, like you don't, look under a microscope and see them or anything like that, but you see their effects in terms of the way that other particles are disturbed by their presence, for example.
There's one more question. Can we use muons instead of electrons for electricity since they have the same charge?
Oh, that's a fun question. I never thought of that. Well, the short answer is no, because muons have such a short lifetime. First, we'd have to produce them, but then they would decay. I mean, I'm sure you can generate a current with muons, but for practical purposes, because they have a finite lifetime, they would just end up decaying down to electrons anyway. Adi, did I get it right?
Yeah, sure. We have electrons available free in materials called conductors. So let's just use them. Yeah, that's all for now.
Thank you. Those are cool questions. Okay, so now to the experiment. So I gave you a little bit of the physics, the standard model, particle physics, whatever, the muon. And now this is like the whole point of the talk, is to talk about this experiment, which has caused so much buzz in the community. Here's the building at Fermilab where the experiment is housed. It's pretty humble accommodations, but look at that sunset. So those prairie sunsets are really amazing. Okay, now the Fermilab collaboration wasn't the first to measure the magnetic moment of the muon. And well, back in the 50s, people, like I said before, people were studying the muon because there was some idea that maybe the muon had substructure because it's so much heavier than the electron. So that was part of the motivation. And then, of course, later on, we learned that it's a fundamental particle, as far as we know. Anyway, from 1959 to 1979, 3 experiments were done at CERN making this measurement. And there were a few measurements made in the US also. At the time of these experiments, both the theoretical calculations and the experimental measurements had big error bars. So these CERN measurements validated the theory of the time. There was no discrepancy at the end of the final CERN experiment. So like that plot thing that I showed a few slides back with the 2 data points, how there was a gap between them. Back when these CERN experiments were done, there was no gap. There was enough of an overlap where there wasn't a sense that there was, really any new physics there, or that the calculation needed to improve at all. So after the CERN experiments wrapped up, advances in the standard model calculation slowed to the point that physicists couldn't justify doing the experiment again with improved precision because they would just be comparing their measurement to the same old number and not really able to glean much from that. So this part of the story really illustrates, I think, the importance of the interplay between theory and experiment, especially in particle physics. This has always been the paradigm that's at play here. So this measurement wasn't made again for almost 20 years when it was made at Brookhaven. Now, if you notice the schematic from the last CERN experiment, there it is, the ring. That design is very similar to what was done here almost 20 years later. And I will explain a bit about what the ring serves in the measurement, because a lot of the photos surrounding this experiment show the ring, but don't necessarily tell you what it does. But anyway, the measurement of the magnetic moment of the muon made at Brookhaven hinted at an intriguing discrepancy between theory and experiment that I mentioned a few slides back. And like I said, it was only a hint, not really a confirmation, because not enough data was taken to be sure. So another measurement was needed. But the Brookhaven accelerator could only do so much. They couldn't produce enough muons to improve the measurement, which is where Fermilab comes in. Fermilab is able to provide the required beam intensity. So in 2013, the main magnet of the Brookhaven experiment was loaded onto a barge and shipped west. And here it is arriving at Fermilab. That's Wilson Hall. Big crowd there. Here are some other photos from that journey that I think are really nice. All right. So after all that fanfare, all that press and excitement, the ring sits in a parking lot for a while. But then it gets installed in the experimental hall between all this yoke steel. So those silver rings that just went in, those are the superconducting coils. Those were the rings that were transported. And that red like UFO thing that was holding it together, that was just a frame. That's not actually part of the experiment. And here you see the yoke being assembled. This yoke steel that encapsulates the superconducting coils weighs over 600 tons. And that also had to be transported from New York to Illinois. So it's pretty mind-boggling. Okay, so this is around 2014. The ring is put back together. Of course, there's still a lot more to be done. And then by June 2015, the ring was cooled to superconducting temperatures, which are around 5 Kelvin. And that is minus 270 degrees Celsius. So very cold. And the cooling is done with liquid helium and liquid nitrogen. All right. So what does the ring do? Well, one thing to note, this experiment is not a collider experiment. I think that a lot of the most famous, most well-known particle physics experiments are like the LHC and the Tevatron, but those were collider experiments. And what we're doing here is different. We aren't smashing particles into each other. Instead, we are taking particles, we're taking muons, and storing them in a magnetic field so that we can observe their behavior. And in this specific experiment, we let the muons do their thing, and actually we catch their decay products, which are positrons. And I don't know if I have said this yet, but positrons are just positively charged electrons. So we just catch those decay products, and that's the main gist of the experiment. All right, then the magnet here, this is showing a cross section. This is a C-shaped magnet with a field strength of 1.45 Tesla. That is about the strength, same strength as an MRI magnet, I believe. And this magnet is designed to accept muons in a narrow momentum range, which is crucial for the measurement. The highly uniform magnetic field is generated by the well-traveled superconducting coils. So these little red rectangles indicate the position of those coils coming into the diagram they're going around. All right. So here it is all put together. Fermilab E989, that's the name of the experiment at Fermilab. Right, so from 2013 to 2018, this whole thing was assembled, which seems like a long time, but when you think about everything that had to go into it, it's actually quite impressive. Lots of subsystems, lots of equipment, lots of amazing engineering going on in this room, in this ring of only 50 feet in diameter. Then in 2018, data taking begins. And every year since, we've had a run of data taking. Each year is called a run. So 2018 was run 1, 2019 is run 2, and we're expected to make a total of 5 runs. We're currently on run 4. And the first result was published, like I said, on April 7th. More data currently being analyzed, right? One thing I'll mention about this, like I said, it's not a collider experiment. It's which are thought of as experiments that like push the boundaries of energy. This is a precision physics experiment. So we're trying to measure something to a really high precision, shrink those error bars. And with this particular quantity, we're measuring it to 12 digits of accuracy, which is like measuring the distance around the Earth to a precision a little smaller than the thickness of a sheet of computer printer paper. So try to do that and see how it goes. Okay. To get G-2, we need 2 main ingredients. We need to measure the frequency of the muon spinning around the magnetic field, and we need to measure, excuse me, we need to measure the magnetic field felt by the muon beam. So at the top here, I'm not going to show a lot of plots or equations or anything like that, but you see that there's this wiggle we're counting the positrons that come in, and the way they come in, they carry this information about the muon spin that's processing, and we can measure that frequency from this wiggle. And then the magnetic field is measured really precisely, and it's combined with the distribution of the beam. So on the left here is the field map in the beam channel, and then on the right is the distribution of the muons. So this is actually kind of like a cross section of the muon beam. All right. So simple enough. Just measure those things and then you can get the answer. And how does it actually work? We start with protons, which are thrown at a target to create pions. Then the pions decay to polarized muons. There they are. When the beam is clean of proton and pion contamination, the remaining muons are injected into the storage ring, where they are contained with that highly uniform magnetic field, and they travel in a circle. There they go. Okay. And while they're traveling around, their spins persist, like I said before, because G minus 2 is non-zero, because G is not equal to 2, and there's that little leftover amount. When the muons go around the ring, the angle between the spin and the momentum, or another way of thinking about it, the angle between the spin and the direction of travel is changing over time. If we lived in a universe where G equals exactly 2, the spin and the direction of travel would stay parallel all the way around the ring. But that's not the case. So we have this changing angle, and that's what we're trying to measure. All right. So after circling the ring many times, muons decay to positrons, those positively charged electrons. And the energy of these positrons is correlated to the direction of the muon spin. So when that child positron comes out of the parent muon, it's carrying some information about the parent muon. And the positron falls out of the ring. It doesn't have as much energy, so it doesn't stay in orbit. So it falls out of the ring, and it gets caught by one of our detectors, where the energy and time of impact are recorded. There we go. So that's the whole story from start to finish. And really, we're just concerning ourselves with the ring section of this diagram, where all the magic happens with the muons. Okay. I think this, the exact way we do this measurement is a little tricky to understand, because it's not like measuring a length or a temperature or something. We're kind of measuring one thing as a proxy for something else. So it's a little, I think it can be a little confusing. But what I have here is an animation of spin. Muon spin is represented by the blue arrow. As the muons go around the ring, like I said, the spin direction is changing constantly. And this graph here is the distribution of the positron energy. So you can see that the energies are fluctuating as the spin is rotating, and that shows the correlation. And that's how we are able to make this measurement, because of that correlation. All right. Okay, here's the, I was gonna say to scale, it's not to scale, those are not protons to scale. Here is a photograph of the cartoon I showed a few slides back. So the recycler ring is where the protons are accelerated, and then they go down, and you have the pions, and there's a smaller ring where the pions are kind of melted away, and we end up with muons. And muon campus is where this ring lives. Okay, so for the rest of the talk, we're going to be concerned with what's in and around this ring. That's where this experiment really happens. All right. First, we have to get muons into the ring. Around here in the yellow box is an object called the inflector. What this does is it cancels the magnetic field in a small region, just enough to create like a little doorway for the muons to come in. So like I said before, the whole superconducting ring, it makes this strong magnetic field to keep the muons in orbit. But to get them into the ring to begin with, you actually have to kind of create like a little hole in the field so you can get them in to begin with. And that's what the inflector does. It cancels out. It's a superconducting magnet that's cryogenically cooled, and it cancels the ring's field in a small window. Now, when the muons are injected into the ring, they're not quite on the right orbit, unfortunately. So we need to put them on the right orbit. If we don't, they'll just like fall out of the ring, and basically the experiment is impossible. In the red zone here, there are these things called kickers, magnetic kickers, and they provide up a magnetic pulse, and they basically do what they sounds like. They kick the beam onto the right orbit. So in this diagram on the left, you can see the original injection orbit, and then when they're kicked, they're moved the 10.8 millirad into the right orbit. Unfortunately, a lot of these things are really hard to photograph because they're just like these long pieces of metal, and they're reflective, and they don't photograph well, and they don't fit in like a camera's frame, I feel. But this stuff is really cool to see in person if you ever get the chance. Okay. Now, keeping the beam focused is done with electrostatic quads. These are quadrupole plates that provide a focusing electric field. They keep the beam focused vertically, so the magnetic field provided by the ring gives us radial focusing, keeps the muons in a circle, and then the quads provide vertical focusing, which keeps the beam from like kind of spraying open, you know, like water in a hose going out that way. It keeps the beam short and concise. The quads cover about 43% of the storage ring. They're inside the vacuum chambers. They're inside where the muons travel. And one special thing about this experiment is that we are able to inject muons at a certain momentum where the electric field contribution to the spin precession actually canceled out. So we only have to worry about measuring the magnetic field. And that's a little detail, but it's very amazing that nature has just provided us with this coincidence that lets us do this experiment much easier. All right. Now, the muons have been injected, they've been kicked, and they are being squeezed by the quads. Now they'll travel through the magnetic field. So on G-2, there was kind of like a field team and everybody else. And the field team did this amazing thing where they took this huge hunk of metal and they made it produce an extremely uniform magnetic field. And it's really, really amazing how they did that, really impressive. They made adjustments to the yoke, to the pole pieces, to the wedges in between the yoke and the pole pieces. And they spent, I don't know how much time doing this, but literally cutting up little pieces of iron foil and putting them on the magnet in the places where small amounts of additional material were needed in order to get this uniform field. So yeah, here again is the cross section of that C magnet. And you can see all these places where there's material that could alter the direction and the strength of the field, and they're tinkering with that. And incredible uniformity was achieved, better than Brookhaven. So I'll play this again, actually. The red line is the Fermilab field as it's getting tinkered with and smoothing out and more uniform over time. The bottom shows you what year it is. So it took them, I guess, about a year to do this. And the blue is the Brookhaven field for reference. So we did much better than Brookhaven. Cool. All right, the last piece of equipment I'll talk about are the calorimeters. These are the detectors that catch the muon decay products. They catch the positrons that are carrying that correlated information. So because the positron energy spectrum oscillates at the spin precession frequency, we get data that looks something like this in the lower right. You see that wiggle there? That wiggle is the spin precession frequency. Yeah, these calorimeters are cool. They are pretty small. They're made of lead fluoride crystals. There are 24 of them around the interior of the ring. So we don't get 100% coverage. We're not catching every single positron that comes out, but we do catch enough to make this measurement. Okay, so that's some of the equipment and some of the machinery technology that goes into it. On the other side of the wall from that big blue ring is the control room. And the control room is pretty humble. It's just a bunch of monitors and like uncomfortable desk chairs. But that's where all the magic happens. It's monitoring this experiment while it's running. And there's a team of really dedicated people on this collaboration. These photos don't show all of them. The collaboration is about 200 people. But these pictures are good because they feature members of the UIUC team. So yeah, those are the people that do the physics. All right. After run 1, we analyzed the data, and what did we get? Turns out the Fermilab measurement actually agrees with the Brookhaven measurement. So you can see the Fermilab measurement is the red and the Brookhaven is the blue. They are in pretty good agreement. But both measurements are dominated by statistical error. What does that mean? Statistical error rather means we need to take more data. So the more data we take, the more these error bars will shrink, and hopefully we will get a more precise estimation of what that number really is. Now, comparing it with the standard model, that deviation, before it was 3.6, it's grown now to 4.2, which gives us more confidence that this is a real effect and that the standard model really is missing a piece that the muon magnetic moment is picking up on. Another thing I'll say, the fact that the Fermilab experiment confirmed the Brookhaven experiment, it gives us confidence that, Brookhaven didn't mess up, and these are 2 separate experiments, even though they're the same experimental design principle and some of the actual hardware is the same. They're 2 very different experiments in a lot of ways, and the fact that these agree is pretty confidence boosting. All right. Now, is muon G-2 alone in challenging the standard model? No. There are lots of other, there are quite a few other measurements, I'll say, that are like this. There are these sort of esoteric parameters that if you're not a particle physicist, you would never necessarily care about or have heard of. But they tell us something about the fact that they tell us something about our theory, that maybe it's predicting the wrong thing or predicting the wrong number. There are a few cases of this. You can see most of them are around the 3 sigma level, which, like I said, is not quite enough to really say definitively that it's meaningful. 5 sigma is our standard for that. But regardless, we know the standard model is incomplete. And so theory and experiment will continue to search for physics beyond the standard model. Okay, what comes next? All right, like I said, so Fermilab, the Fermilab experiment, muon G-2, has to continue to take data and analyze data to build confidence in the result, which we are doing. Another thing that can happen to improve confidence in this number is an independent measurement. There is an experiment in Japan being proposed, or it has been proposed, but it hasn't been built yet, that uses a completely different experimental method. It doesn't use a ring. It has like a chamber, and muons are injected and slowed down, and they measure the spin a completely different way. So if this experiment rather comes online and confirms what we found, that is very promising, and that gives us a lot of confidence that the measurement is correct. On the theory side, in what the theory community has to do is to continue to work on the calculation and reach a consensus and shrink those uncertainties. I didn't show anything about this because I don't know much about it, but there are a few theory papers that have been published that have given contradicting predictions. So even though there's the main consensus that we're comparing our number to, there's some other ones out there that use different methods and different data. So that's, part of the process of the science is this iterative back and forth and comparison, and hopefully narrowing down those errors and understanding what's really going on. So for our part, for the Fermilab experiment, we are taking more data. Like I said, the data that we took so far, or that we published so far, is run 1, which is just the red portion of this graph. And that is basically all of the data that Brookhaven took is equivalent in terms of quantity to run 1. So by analyzing our next few data sets, we're going to significantly improve the measurement. And hopefully, 22, hopefully we'll have a really good result in a year or two after we analyze. We're currently analyzing run 2. That's what I'm working on right now for my dissertation. And run 3 is being processed. So hopefully not too far in the future, we'll have a much better result to share. Okay. Finally, what could this all mean? Like I said before, if we continue to verify these results, we continue to build confidence that we didn't make any mistakes, then this leads us to believe that the discrepancy between the standard model calculation and the experiment is a real discrepancy, and meaningful. It means the theory is incomplete. The theory is not calculating everything that's out there. And so a new theory or an addendum to the standard model is needed to address that missing piece. Unfortunately, the thing about Muon G-2 is there are lots of candidates for what Muon G-2 could address. And Muon G-2, our particular result, it doesn't really narrow down the field that much. There are lots of things that are possible still. So really more data needs to be taken. Theorists will continue to work on this, but it's exciting. What new laws of nature have we yet to discover? What new particles or forces could be hidden in plain sight? We know, like I said, the standard model is incomplete, and there's finding out what else is out there. It's just a matter of time. So hopefully Muon G-2 can provide that crucial clue in solving these mysteries. Okay. So if you are interested in learning more, I would say, well, our paper is up on the archive. You're welcome to read it and all the gory details. But also the Fermilab YouTube channel has a lot of good videos, just in general. I think they do a really great job at outreach, but they've also done a pretty short video that talks about our first results. So it's a little bit of the science and a little bit of the like hubbub around it. That's worth watching if you want to get a recap. I highly recommend this comic strip, the full comic strip. This is just a piece of it by PhD Comics. You can just search, on your search engine of choice. Again, that explains the physics really nicely, I think. And finally, I'm just going to plug the Fermilab Physics Slam, which is tomorrow. It's a free virtual event. And that you can also find by just searching online, Fermilab Physics Slam. One of the presenters is going to talk about Muon G-2. And the thing that's special about this event, it's not just like another public talk. It's it's more like performance-y kind of. So I think it should be really fun. And if you're interested in G-2 or more about what Fermilab does, I highly recommend going to that. All right. Thank you for watching, being here with me. I'm ready for any questions.
Thank you. Yeah, such an exciting result. Thanks for the wonderful talk. So we have a couple of questions in the chat. Hold asks, how are muons used if they have such a short life?
Right. So we harness the magic of relativity. We accelerate them to a high enough momentum where time dilation kicks in, which is a relativistic effect. And so in the lab frame, they have a longer lifetime. And yeah, we're able to get enough turns around the muon ring to study them.
Yep. There's one more question. Does the muon have positive charge? Otherwise, where does the positive charge of the positron come from when the muon decays?
Good catch. Okay, very good catch. Yeah. So in the experiment that we've done at Fermilab, we're using the positive muon, and which is, you would call it the anti-muon, I guess. This experiment can be done with both the positive muon and the negative muon. At Brookhaven, it was done with both. So yeah, I kind of like glided past that detail. But if you were to do this experiment with the proper muon, the negative muon, then you would get an electron out. And since we do it with the positive muon, we get a positron out.
If you have any more questions, just type them in the chat. So I have a question. So what's the future of the experiment? Is the experiment still running, or how long is the experiment planned to run?
Yeah, the experiment is still running. We're taking data right now. We're in run 4 currently. And the goal is to take, the goal originally that was proposed was to take 20 times as much data as was taken at the Brookhaven experiment. I'm not sure if we will achieve that, but that's our goal. We are likely going to run until or through 2022. And I think, well, the reason I think we wouldn't run indefinitely, there is another muon experiment coming online called Mu to E. And so they're going to start needing muons eventually. And that will mean the end of muon G-2. But yeah, the G-2 is still extremely active and analyzing lots of data and taking data.
No further questions. Oh, there's a question just now. Do you have a guess or a favorite theory for what new physics the G-2 result reflects?
Yeah, I don't. Unfortunately, I used to like kind of read more up on like new physics before I was in grad school when I had more time. So I really don't have a preference. I think they are all kind of equally likely. I don't know. Adi, do you have a favorite?
No, I do not either. I would like to see more data coming from the G-2 experiment, and there are also efforts going on the theory side. So I would just like to see how this battle or this tension between theory and experiment goes in the next few years. Yeah,
it's exciting because there are quite a few people who still think that like, oh, it's just a fluke, it'll go away. So it really is interesting. But yeah, I don't know what it means. I think yeah, Muon G-2 is just one possible hint of what the new physics could be. We probably have to make more measurements going forward once we've confirmed that this is meaningful.
Well, so what are your favorite parts or experiences of working on this experiment? Or favorite memories?
Yeah, I really liked, it's funny, I was looking in our internal document database recently, looking for photos, preparing for this talk, and I found like, I found a document from like 2014 or 2015 of working on the quads. There are just so many things, and I forgot I had worked on that with Muon Wei and Joe Grange and Jason, the whole team. And it was just like fun to look back and think of all these ways that you've touched the experiment, like whether it's just putting a cart in its proper place or cleaning down some piece of the magnet with alcohol. Like, I don't know, it's been fun to actually put hands on the experiment, while the kind of all the glory goes to the data and the analysis. I've really enjoyed you know, using a wrench and like wiring things and stuff like that. That's been fun.
Thank you. I don't see any more questions in the chat. So thank you again, Cristina, for such a nice talk. And thanks to everyone for tuning in. I hope you enjoyed the talk. And if you have any questions, feel free to ask right now or wait until the next time. Well, thank you.
Thanks, everybody.